Excitation-contraction coupling begins at the motor end plate when acetylcholine is excreted from the synaptic knob and diffuses into the motor end plate. Here, the acetylcholine binds to an ACH receptor on chemically gated channels. Once bound, sodium rushes into the muscle fiber and potassium slowly exits. If enough sodium rushes in, threshold is reached and an action potential begins. The high levels of sodium polarize the membrane, making it more positive. A voltage-gated sodium channel, opens, allowing more sodium to rush in. This polarizes the next part of the membrane enough to open a voltage-gated potassium channel as well as the following sodium channel. Once opened, the channels slowly close, which can be compared to a faucet. Imagine the faucet is initially opened wide, but then slowly closed off, obstructing the flow until it is completely closed. The sodium channels continue to propagate, allowing positive charged sodium ions to rush in, while the potassium channels diffuse potassium to the extracellular matrix, depolarizing the membrane, and ultimately leading to it being at resting state again. Initially, the intracellular ratio of potassium to sodium was high, but as the action potential moves along the membrane, or sarcolemma, this changes dramatically. The sodium-potassium pump works at a slower rate to bring these numbers back to normal. Going back to our action potential, it continues and reaches the transverse tubule, where voltage-gated calcium channel leading to the sarcoplasmic reticulum are located. It is from the sarcoplasmic reticulum that calcium diffuses out through release channels triggered by the opening of the voltage-gated ones. From here, calcium is released and can bind to troponin, beginning contraction.